The second statement that we'll be covering is Clausius' statement of the second law. And this will be dealing with refrigeration cycles. Before we start, we need to understand what is a refrigeration cycle. On this video, you can see a basic fridge.
Hi, I'm Matt from eSpares. In this video, I'm going to show you how a fridge works. And we all know it's important to keep fresh food in the fridge. The bacteria that can cause food to go off can't really thrive below about 5 degrees C, so keeping our food in the fridge keeps it fresh for longer. Now, the process of refrigeration is actually quite a straightforward one. If you lick the back of your hand and then blow on it, it starts to feel cool straight away. And that's because as that liquid evaporates off into a gas, it draws heat away from the skin. And in a fridge, we've just got a continuous process where a refrigerant is being allowed to turn from a liquid into a gas and then being turned back into a liquid again. Let's take a look at the back of this old Zanussi fridge freezer, and we'll start down here with the compressor. It's essentially an electric pump which is pushing a refrigerant around a closed system, first along the outside of the fridge, then the inside of the fridge, before finally returning back to the other side of the compressor to continue the cycle. Now, in the old days, they used to use ammonia as the refrigerant, and that was quite toxic. They then changed to Freon, which you may remember is the stuff that did the damage to the ozone layer. This fridge freezer uses isobutane. It doesn't really matter what the refrigerant is, it just needs to be a substance that can easily turn from a liquid to a gas and back to a liquid again. So starting on the high pressure side of the compressor, our refrigerant gas gets very hot, much like a bike pump gets hot as you put the air under pressure when you're inflating a tyre. And that heat is radiated away in this condenser coil. It's like an ordinary household central heating radiator. And you can actually feel when it's on that it's very hot on this side, getting cooler as you move across, so that by the time it's over here, our refrigerant has cooled down sufficiently to be condensed into a liquid where it goes and sits in a reservoir at the bottom of the appliance. Our liquid refrigerant then passes into this thing, which is called a filter dryer, and that just traps any contaminants, removes any moisture, which is important because the refrigerant now passes into this, what looks like a wire. It's actually a very fine capillary pipe, and that feeds up to the inside of the fridge to the evaporator coils. Now, on your fridge and freezer, you may not be able to see the evaporation coils. They're probably behind a panel at the back or in the top of the unit. But on this hot point fridge freezer, you can actually see the evaporation coils here. They form part of the shelf structure. So after passing through that fine capillary, our refrigerant liquid passes into this much larger diameter coil where it's allowed to expand and evaporate into a gas. And that draws the heat away from inside of the unit. Now, at this point, the pump or compressor is now drawing that gas through the whole system to be recycled and used again. Everything's encased in a very thick layer of insulation to make sure that the only heat that's drawn away is from the contents and the inside of the freezer. Most fridges would be cooled by evaporation coils in exactly the same way, although on some fridge freezers, cold air is simply drawn up from the freezer unit into the fridge. Now, the big problem with the whole refrigeration process is that every time we open the door, we let moist air in, and that moist air condenses into water, which needs to go somewhere. On a fridge, it condenses onto this back panel where it drains down and out through this drain hole. And in the freezer compartment, that moisture builds up as frost. In a freezer like this, you'll need to manually defrost by turning it off and draining away the water as it melts. On a frost-free or auto-defrost freezer, the compressor will periodically stop, and there are heating elements around the evaporator coils which will heat up, melt away the frost, and that water will drain away at the back of the appliance. And all that water ends up in this evaporation tray. That just sits on top of the compressor, so it's nice and warm, and that just evaporates all that water away. So there we go, that's how a fridge works. Now if you need any spare parts for a fridge or freezer, you can find them for all makes and models on the East Bears website. Thanks for watching.
From a thermodynamical point of view, we can sketch this as we can provide work with the compressor. Then we have a condenser here. This is state 1, this is state 2, and it's moving in this direction, so anti-clockwise. Reaching here, we have kind of a valve, okay? And then we have our evaporator. This valve, this is like the coil that you see at the back of your fridge, okay? And sometimes you have a significant decrease in the size. This will lead to a decrease in pressure and temperature at the same time. So this is state 3, this is state 4, and we go back to state 1, and this is an evaporator. So here on this refrigeration cycle, we are providing work here, which is the work of the compressor. Here we are rejecting heat. This is a Q out, and here nothing is happening. We'll see that we can easily see that the process here conserves enthalpy. H2 is equal to H4, and here we're having a Qn. So basically your food is here and your cabinet is separating the two. So you are taking heat from your food. This will allow your substance to evaporate. It's compressed and then goes at the back of the fridge, and then you are rejecting heat. So this is why when you put your hand at the back of the fridge, you feel this heat, which is a Q out. And then you continue the cycle. So what is important here to see is that the only way for the cycle, this refrigeration cycle, to work is to provide the work of the compressor. If you don't provide the work at the level of the compressor, there is no way for you to construct this cycle. Meaning that you have to plug the fridge, okay? Otherwise, you cannot run your refrigerator. But this actually is really fundamental, okay? Why? Because what your fridge is trying to do, the food, let's say, is 4 degrees C. The back of your fridge is, let's say, it's the room temperature, let's say 23 degrees C. And your fridge is trying to move heat from cold to hot. Well, we know that going from hot to cold, this is spontaneous. There is no price to pay. But your fridge is trying to go against this by going from cold to hot. And there is a price to pay. And this price to pay is the work of the compressor. We can also evaluate the performance of a refrigeration cycle. And this performance is by dividing. What do we want to maximize here? In a refrigeration cycle, you would like to maximize Qn, the heat that you are extracting. So this getting cooler, okay? So Qn. And what's the price to pay for this to be done? We are using the work of the compressor. Well, typically this ratio between Qin and the work of the compressor is higher than 1 for refrigeration cycle. So this is why we don't call this an efficiency, okay? We call this a COP, or coefficient of performance. And this will tell us how efficient is your fridge. So, meaning that Clausius statement of the second law of thermodynamics is simply telling us that if you want to go from hot to cold, it's a free ride. Okay, my cup of tea will cool down spontaneously. So basically, if I leave the room and come back and the temperature of my tea went down, so it's fine for me. I won't suspect anybody. But doing the inverse, meaning going from cold to hot, there is a price to pay. And this price to pay is work. So now, if my cup of tea is, let's say, at 40 degrees C, I leave the room and come back and it's 80 degrees C. So for me, somebody has touched my cup of tea, okay? Heated up my tea or whatever. I cannot imagine the tea by itself spontaneously to heat up, while the inverse is possible, okay? So this now leads us to the formulation of the Clausius statement of the second law of thermodynamics, which is, it is impossible to construct a device that operates on a cycle and has no effect other than the transfer of heat from a low temperature body, to a high temperature body, So what does it mean? It is impossible again. So you see, it's a very strong restriction to our ability to design systems. It is impossible to construct a device that operates on a cycle. So you see, it's a cycle. And has no effect other than the transfer of heat from low temperature to high temperature body. What does it mean? This means that you cannot design a refrigerator and claiming that your refrigerator is transferring heat from the inside of the cabinet to the outside without having work in, so without plugging your fridge. So a violation of the second law of thermodynamics Clausius statement is sketched this way. So assume we have two reservoirs, one with T low and one with T high. So I claim that I can transfer heat, Q, from low temperature reservoir to high temperature reservoir, T high, but I don't have any other effect. It's the only effect. It's the heat transfer between T low and T high. Okay, so meaning I'm claiming that I can heat up my cup of tea without any heat source from the outside, okay? So now to avoid violating the second law of thermodynamics Clausius statement, what we have to do, we have to provide work in. Now we have another effect. Except the heat transfer, we have work in. So therefore here we plugged the fridge. We are paying for the electricity required to turn to run your compressor. So this is a schematic of the Clausius statement of the second law of thermodynamics, that you cannot go from cold to hot without paying a price, and this price has to be an energy in here in terms of work in.